Hi everybody. In the last video we talked about how you can use algebraic information to come up with the graph. In this video I want to talk about how we can use some information that we read off the graph, such as the vertex or the x-intercepts, to come up with an equation. So we're going sort of in the opposite direction. So let's do an example. First we want to find an equation for a parabola that has a vertex at 2, 3. Well, you might tell me that this is pretty easy because we know the vertex form is just f of x equals a times x minus h squared plus k, where h comma k is the vertex. So in this case, h would be 2 and k would be 3, so I can just plug it in. So here's an equation. X minus 2 squared plus 3. That certainly has vertex 2, 3. But here's another one that has vertex 2, 3. Negative x minus 2 squared plus 3. This one opens upwards and this one opens downwards. So we can actually see that if we graph it in our calculator. So let's do the first one. X minus 2 squared plus 3, and then we'll also graph negative x minus 2 squared plus 3. So this is first showing the graph that opens upwards with the positive value for a, and that's the one with the negative value for a. They clearly have the same vertex, and it's at 2, 3. We can check that by using this second calc value. And if we put x equals 2, the y value it tells us is 3. So how can we specify which parabola we want with a certain vertex? I have to give you a little bit more information, or else you could put any value for a you want and it would have this vertex. So in the next example, we're finding a very specific equation. We want to find the equation, so I can even replace and with the, for a parabola with vertex 2, 3 and through the point 0, 2. I actually jumped the gun a little bit by switching it to the, because we know we need 3 points to determine a parabola. So we really are just finding one possibility. But this will specify a value for a. So if we have f of x equals a times x minus h squared plus k, what we need to do is first substitute in the vertex. And then we're going to figure out what a value makes us go through the point 0, 2. So we leave a as a variable, and we have x minus 2 quantity squared plus 3. Now we know that it has to go through the point 0, 2. So this says when we plug in 0, we get 2. The y-intercept is 2. So f of x will be 2 when x is 0. And now I have an easy equation with a single variable, a, and I'm just solving for a. So I have 2 equals a times negative 2 squared, which is 4, plus 3. I'll bring the 3 over, so I have negative 1 equals 4 times a, and so a equals negative 1/4. So I found a value for a. Now I plug it back into this, and I find that f of x equals negative 1/4 times x minus 2 squared plus 3 is the desired equation, the one we were looking for. Let's do a different type of example. In these two, we were coming up with equations where we knew the vertex, and we knew a point. What if I give you two very specific points, negative 1, 0 and 3, 0? You'll notice that these are the x-intercepts. When I plug in negative 1, I'll get out 0 from my equation, and when I plug in 3, I get out 0 from my equation. So this is a little bit tricky unless you've seen an example like it before. Can you think of a really easy equation that when you plug in negative 1, you get out 0? Take another second. So I want to have x. When x is -1, I want it to equal, the whole expression to equal 0. So what if I just have x plus 1? Plug in -1 for x. -1 plus 1 is definitely 0. So this is a great place to start. We want to have x plus 1 as part of our expression, and we want it in such a way that we have x plus 1 times some other stuff, so that when I plug in -1, it doesn't matter what this other stuff is, I'm still going to get 0. I also need to make sure that when I plug in 3, I get 0. So a really easy expression that I could multiply x plus 1 by is x minus 3, because this term will be 0 when I plug in 3, and this term will be 0 when I plug in -1. And I could multiply by anything else I want here. So you could put like a 2, for example. I can't put 2x. That would be bad, because then it's not quadratic anymore. Then you end up with x cubed. So no x's, but any constants you want can go there. So let's have a look and make sure that this works. Let's actually multiply it out so it's in standard form. So I'm going to have 2. Now I FOIL. First is x squared, outer is x, inner is minus 3x, and last is minus 3. So this gives me 2 times x squared minus 2x minus 3. So let's go ahead and graph that. 2 times x squared minus 2x minus 3. We look at the graph. It's a parabola, and we want to make sure that these intercepts are -1, 0 and 3, 0. There's a nice way you can do that using your calculator. If you click second trace 0, it tells you what the intercepts are. First, it's asking for a left bound, so I'll go just slightly left using the arrow. Oops. I've got to get myself into the picture here. Where's my cursor? There we go. It's a little hard to see the cursor. It's right here, so I'm just slightly left of the x-intercept. Now it asks for a right bound, so I go to slightly right of the intercept and press enter. And it tells me that I have a 0 at -1, 0. So that's correct. I could do the same thing to check that this one's 3, 0. I have a video on the calculator resources that describes how to use the 0 function if that went by a little bit quickly. So this definitely works. Now before I end the video, I want to show you what would have happened if I put 2x instead of just 2. So I'm going to put 2x times the expression x minus 3 times x plus 1. And this is not a parabola anymore. We know that because if we had a 2x here, then we would have 2x cubed minus 4x squared minus 6x. This is now cubic, degree 3. So the parent function is the cube function. That's why this looks wiggly like the cube function. We're going to study polynomials of higher degree like this one in the next section of the book. And this example that we just came up with is a polynomial of degree 3 with x-intercepts at, in this case, 0, 0. That intercept comes from the fact that when we plug 0 in, this term goes to 0. -1, 0, since this term will be 0 when we plug in -1, and 3, 0, since that third factor will be 0 when we plug in 0. So this is just a taste of what's to come. We'll spend a lot more time on these polynomials of higher degree. So good luck with the web work, and please come to me if you have any questions.